Hello everyone, welcome to Electrix Lab. Today's video covers STM32 ADC pole for conversion and DMA. Analog to digital conversion, ADC, transforms continuous analog signals, like sound or temperature, into digital values for processing by digital systems. Let's create a project for ADC normal mode. Here, I am using the STM32 AF103c8 MCU. First, I am enabling the external crystal for the clock. Serial wire debug. I am using the maximum clock of the MCU. This microcontroller has 2 analog to digital converters and 10 channels for each. Let's enable the ADC. Since I am using only a potentiometer, I need 1 channel. I am using channel 9 for the potentiometer reading. Enable the continuous conversion mode, or else the ADC will stop after every conversion. There is an issue with the system clock configuration. The ADC clock must be less than 12 MHz. Change the ADC prescaler value to 6. Now it is solved. Let's save the project. Create a variable to store the ADC value. We will start ADC conversion by using HAL-ADC start. Then, call HAL-ADC pole for conversion, which waits for the ADC conversion to complete. Next, get the ADC value and store it in the register. Build the project. There should be no errors. Connect the potentiometer according to the diagram I have provided. Connect the STM32 board to the computer using ST-Link. Upload the code and launch the debug session. Select Live Expression and add the variable where the ADC value is stored. Its reference voltage is 3.3 volts. The raw value should be 0 for 0 volts and 4095 for 3.3 volts. It's working properly. Let's move to the DMA mode. DMA is able to manage memory-to-memory, peripheral-to-memory, and memory-to-peripheral transfers. The DMA controller supports circular buffer management, avoiding the generation of interrupts when the controller reaches the end of the buffer. Let's create a new project and set up the basic configuration the same as before. Enter the commercial part number. Let's configure the ADC for DMA mode. Here, I am using channel 9 for the potentiometer and channel 0 for the IR sensor. Enable the continuous conversion mode. Select the number of channels we are using. Set the ADC prescaler to 8. Let's move on to the DMA settings. Select the DMA circular mode so that the values continue to overwrite the buffer in the background. Set the data width to Word. Let's generate the code. Create a data buffer to store the 32-bit ADC values. We will start the ADC with DMA by using HAL-ADC start DMA. Set the handler, data buffer, and the number of data points we are going to capture. Assign the two variables to the ADC values in the data buffer. Build the project. There should be no errors. Connect the potentiometer and IR sensor according to the diagram I have provided. Let's upload the code and run the debug session. Add the ADC buffer to live expression. it is capturing analog values properly. Thank you for watching. If you found this video helpful, please subscribe to Electrix Lab. Don't forget to hit the bell icon so you never miss an update. Stay tuned for more exciting and informative STM32 tutorials.